You know, we use numbers every single day, but we almost never stop to actually think about them. And it turns out, just beneath that simple surface, there's this incredibly elegant and kind of counterintuitive structure. Today, we're going to uncover 5 truths that'll pretty much change the way you see numbers forever.
Okay, let's just dive right in. We're about to challenge some of our most basic assumptions about what a number even is. And we're going to start with a fundamental question about identity. So here's our first surprising truth, and it's a bit of a mind bender. A simple number you know and love, like 7, isn't just one thing. Nope. It actually holds multiple identities all at the same time, living in 4 totally different mathematical worlds.
And here's how it works. These number sets, they build on each other, kind of like a set of Russian nesting dolls. We started with the natural numbers, for simple counting, like sheep. Then we needed a way to say there were no sheep left, so we invented 0. And boom, you get whole numbers. Then you need to talk about things like debt. So you add negatives, and suddenly you have integers. And all of those fit inside the huge world of real numbers.
So here's the crucial part, this beautiful hierarchy. Because 7 is a natural counting number, it's that smallest doll. It automatically belongs to every larger set it fits inside. So it is simultaneously a natural number, a whole number, an integer, and a real number. It's such a simple idea, but there's a real elegance to that structure.
All right, let's just zoom in on one specific moment in that evolution we just talked about, the invention of 0. It seems so simple now, but this one idea, well, it was so powerful it completely changed the game.
I mean, just look at this. The only thing separating the entire set of natural numbers from the whole set of whole numbers is 0, that one number. That's just how powerful this concept was. The single idea of representing nothing was profound enough to demand an entirely new classification of numbers.
And it absolutely was. This one idea created this fundamental split. It separated the simple physical act of just counting stuff you can see from a way more abstract and powerful number system that could handle much, much more complex ideas.
Okay, let's keep building on this for our next truth. The word irrational sounds intimidating, right? But the concept behind this entire class of numbers is actually based on one very, very simple and elegant rule. This is it. This is the whole secret, the fraction test. It's the key that unlocks the whole mystery. If you can write a number as a nice, clean fraction, it's rational. If you can't, for any reason, it's irrational. Seriously, that is the entire secret. Let's put it to the test. You see the square root of 9, and you might think it belongs with all the other complicated-looking roots. But wait, it simplifies perfectly down to 3. And can 3 be written as a fraction? You bet, 3 over 1. It passes the test with flying colors. So, it's rational.
But now, look at the square root of 7. It's a whole different story. You can't simplify it down to a nice whole number, and there's no simple fraction that equals it. Its decimal just goes on and on and on forever without repeating. It fails the fraction test. And that, right there, is what makes it irrational. Simple as that.
All right, get ready for this next one, because it feels like it breaks all the rules we think we know. In the super precise language of mathematics, not all digits carry the same weight. And surprisingly, sometimes the humble 0, well, it doesn't really count at all.
Okay, take the number 300. In science and engineering, the digits that tell you something real about a measurement are called significant figures. And here, only the 3 is significant. Those 2 zeros, they're just placeholders. They tell us we're in the hundreds, sure, but they don't promise any real precision. That number could just be 298, rounded up. But now, look at this, 3.040. Suddenly, everything changes. In this context, those zeros are not just placeholders anymore. The 0 that's trapped between the 3 and the 4, and that other 0 hanging out at the end, after the decimal point, they are both guarantees of precision. They are telling us this measurement is accurate all the way down to the thousandths place. So you see, a 0's meaning isn't fixed at all. Its position is absolutely everything. Without a decimal point, it can just be a placeholder. But with the decimal, it becomes this vital piece of data, a promise of precision. It's the context that gives the digit its real power. Okay, get ready for our final and I think most stunning revelation. We're about to witness a moment of pure mathematical alchemy, where 2 numbers that look totally chaotic transform into perfect, simple order. So first, let's meet our ingredients. We've got something called a surd. That's just a fancy name for an irrational root, One of those messy numbers whose decimal form just stretches on and into infinity, never ever repeating. Think of numbers like the square root of 2 or the square root of 3.
So, here's the question. What do you think should happen when you multiply two of these infinitely long, non-repeating, just messy numbers together? I mean, logic would suggest you just get an even bigger, more complicated mess, right? Well, let's just watch as this hidden structure reveals itself. We're going to multiply the irrational number root 3 by another irrational number, root 12. Now, the rules of math let us combine them under one root sign, which gives us the square root of 36. And the square root of 36 is just 6, a perfect, simple, rational, whole number. How cool is that? Two infinitely complex, messy, irrational numbers combined, and what came out was the cleanest possible answer. That is mathematical alchemy. And that, right there, is the ultimate takeaway. The numbers we use every day are not just some arbitrary set of rules we have to memorize. They are part of this deeply logical, elegant system where these hidden patterns and beautiful structures are always waiting for us, just beneath the surface. It really leaves you wondering, doesn't it? If the everyday numbers we use are this full of surprises, what other simple rules that we just take for granted might have a much more fascinating story to tell?